Okay, good morning. What we're going to start off with today is electronegativity. And then once we get through electronegativity, we'll go back to doing some of these Lewis structures. Okay, so this is section 8.4, and it's entitled Electronegativity and Polarity. Okay. All right. So thus far, we've talked about covalent bonding, which is the idea that electrons are shared. So for example, if we have a hydrogen molecule, it's formed when each hydrogen atom uses its electron. Remember, hydrogen only has one electron. Uses its electron to form a pair, so that those two electrons are now shared by both the nuclei, right? So remember, the hydrogen atom, of course, is very simple, right? It's got a little nucleus here at the center. It has an electron, which I'll write as a little dot. So you got a little nucleus here with a little dot. And what we're claiming is that now these two dots, these two electrons, are now in the same region of space, and they are now acting kind of like a glue to hold those two nuclei together. So the atoms are held together. And typically we use line notation to represent this sharing of electrons. When we have one pair of electrons shared between two nuclei, we call this a single bond. Okay, and it's an example of a covalent bond. Now, it turns out there's an interesting property of the elements. So all elements have properties, right? They have densities, state of matter, color, conductivity of electricity, conductivity of heat. The elements have properties. They have an interesting property, which is called electronegativity. Okay, that's this word right here, electronegativity. And originally, electronegativity was used to describe the strengths of bonds. There were some, what we might call anomalies to the strengths of bonds that were, people needed explanations for. So they came up with this idea of electronegativity. But today we use it primarily as a way of thinking about the macroscopic properties of matter. So for example, is something, does it dissolve in water? Does it dissolve in alcohol? Does it dissolve in oil? Or is it a really viscous liquid, for example? Does it boil at a high temperature or does it boil at a low temperature? And it's also used to consider, to evaluate Lewis structures. So let's take a look at this idea of electronegativity and polarity. It's related. And here's the idea. If we draw the Lewis structure, I'm going to pick a simple molecule, hydrogen, which is in group 1A, and fluorine, which is in group 7A. Okay, let's draw the Lewis structure for that molecule. It's a very simple molecule. We have a hydrogen atom. It's in group 1A, so it only has one valence electron. Fluorine is in group 7A, so it has 1, 2, 3, 4, 5, 6, 7 valence electrons, right? And fluorine, we would try to impose the octet rule, right? And for hydrogen, we would try to impose or implement the duet rule. And so what happens is a bond is formed between those two electrons, or using those two electrons. And so we have a single bond between the fluorine and the hydrogen. The fluorine now has 8 electrons. That's the octet rule. The hydrogen now has 2 electrons. That's the duet rule. So we got a great Lewis structure here, right? Now, it turns out that if you measure the electrical properties of this molecule, So now we're considering electricity. And how would you do that? Well, here's one way. HF at room temperature is a gas. HF is a gas. So that means that it behaves like a gas. And what you can do is you can do certain experiments where you put the gas into a container and you apply a voltage to it, to the container itself, to the walls of the container. So like right here, we're going to apply a positive voltage. And then over here, we're going to apply a negative voltage. Okay. So you have some sort of power supply, applying voltage. And what is observed is that the HF molecules they're gas molecules, right? So they're bouncing around inside this container, right? Just like a gas. But what's observed is they tend, on average, even though they're able to spin, on average, they have a particular orientation. And the orientation is that the hydrogen is directed towards the negative potential here on the left. And the fluorine atoms are oriented towards the positive potential on the right. So again, they are gas molecules, so they're bouncing around and they're changing their orientations. But on average, what's observed is the fluorine atoms are directed or oriented towards the positive, and the hydrogens are attracted or oriented toward the negative. The only explanation for that is that the HF molecule has electrical properties itself, right? So if you have something that is electrically neutral and has no electrical properties, like a neutron, for example, it is not affected by electric potentials. It's not affected by voltages. Insulators, for example, are not affected. But the HF molecule is. And so from that, we have to conclude that it has some sort of electrical property internal to the molecule. And it turns out that internal property is this. The reason that it orients itself in the direction that it does is that there is, at the atomic level, a negative charge associated with the fluorine atom. It's negatively charged. And the hydrogen is equally positively charged. So there's a positive charge associated with the hydrogen atom. Now, overall, it's neutral because the amount of positive charge the hydrogen has is equal to the amount of negative charge that the fluorine has. So overall, it's not an ion. It's not like it's overall negative or overall positive. It's neutral. But internal to the molecule, there are charges associated with the individual atoms. And so what happens then is that when you have charges that are separated by a distance, you can model that with thinking of just a little stick with a negative end and a positive end, right? And we call this an electric dipole. D-I-P-O-L-E, two poles, right? If you look at it, it's like a pole. It's a line, and then it has two ends, so it's a dipole. And because these ends are charged, they're not masses, so it's not like you have mass on one end and mass on the other. You have charges on either end, so it's called an electric dipole. Okay, there are also magnetic dipoles, but we're not going to worry about those. So this HF molecule, even though it's neutral, has electrical properties. And what happens then is the positive end of the hydrogen atom is attracted to, this negative potential, right? There's an attractive force occurring there. So on average, the hydrogen atom is going to be attracted, right? Because positive is attracted to negative and negative is attracted to positive. On the other hand, the fluorine atoms, because they have a negative end, they are going to be attracted to the positive potential. And if you were to change the voltage, right, like if you were just to flip this power supply around, just change where you're connecting the wires, make it the opposite, you would find that the molecules on average would flip as well. They would change their orientations so that the hydrogens are attracted to the negative voltage and the fluorines are attracted to the positive voltage, okay? So that's sort of a simple explanation of this thing. It's called an electric dipole. But we have different terms. As you've noticed in chemistry, we have different terms for the same thing. So colloquially, we just call it polarity. That's what chemists call it. They call it polarity, but really it's electric dipole. The molecule has an electric dipole, which means it has this electrical property of separated charges, but we call it polarity. So we would say that HF is polar. That would be another way of saying it. So we would say that there's polarity in this molecule or bond polarity, but we would also say that HF is polar. More technically, we would say that HF possesses a strong electric dipole. So what we want to do at this stage is we want to be able to make a prediction about molecules, meaning if I see a molecule and I draw its Lewis structure, how do I know whether it's going to have this electric dipole or not? Some molecules have them, some molecules do not. So how do we know? So this is really the issue of just sort of predicting whether a bond is polar or not. How do we do that? How do we predict that? So it's called electronegativity. And there is essentially a periodic table, a version of the periodic table that contains electronegativity values. Okay, so I'm going to actually, let me show you one. I'm going to use some numbers on this, but let me just save this here. And I'm going to stop share, and then let's come over here. And let's do electronegativity table. We should be able to get an image of this pretty quickly. Here we go. This one's a nice one. Ooh, this is a nice one. Okay, let me share this one. Every once in a while, you get one that's really nice. Okay. Do need a bigger screen. There we go. Okay, so here is the periodic table. It's not complete. Notice there's some elements that are not there. And instead of giving us the molar masses of the elements, it gives us electronegativity values. Okay, so take a look at the numbers. So those are the numbers underneath the symbols, right? So hydrogen, let's start with element number 1. Hydrogen is 2.20. Okay, so it has an electronegativity value of 2.20. That number is unitless. Don't worry about units. You don't actually do much in the way of, we don't use it to calculate much. Just look at simple differences. Let's take that first column, the alkali metals. Hydrogen, lithium, sodium, potassium, rubidium. Notice the pattern. It's 2.2 with hydrogen, but then when you go to the next element underneath it, lithium, it drops all the way down to 0.98. That's a pretty big drop, right? It went down by more than 50%. And then it continues a trend of going down, right? Of decreasing, but not so much, right? For example, lithium is 0.98, sodium is 0.93. So it's a small difference, but there's a little drop there. And then potassium, a little drop further, and then rubidium a little bit further. And you get all the way down to francium. This is actually the first table I've ever seen that had francium value, because I don't even know how they do that, because francium, it has been estimated that there's no more than 10 to 15 atoms of francium on the Earth at any given time. So I'm not sure how they calculated that or measured it. It might be calculated and not measured. Let's see. So anyways, The pattern is it decreases as you head down. And you can see the same pattern holds for the second column, the alkaline earth metals. Beryllium is 1.5, magnesium is 1.3, calcium is 1, strontium is 0.95, so forth and so on. So it decreases within a family, right? Remember, those are called families, right? The column is a family. They all behave similarly, so they're called a family. So lithium and sodium are similar. Beryllium and magnesium are similar, although beryllium and magnesium are more different. Magnesium and calcium are pretty similar. Then you see the transition metals, and you kind of look, see if there's any patterns for transition metals. And there's still one there, which is within a column, within a family. It does decrease as you go down, right? So for example, scandium, number 21, is 1.36. Yttrium, right beneath it is 1.22. And lanthanum below that is 1.1. So it's continuing that pattern. And then you get over to the P block, right? The right side of the table. Boron, higher than aluminum, higher than gallium, higher than indium. It decreases as you go down. Carbon, silicon, germanium. Again, this pattern. Now notice there's an exception here, right? Like if you look at germanium, which is number 32, it's actually higher than silicon, which is 1.9. So there's a couple of exceptions in there. There's one anyways. Nitrogen, 3.04. Phosphorus, 2.19. Arsenic, almost exactly the same as phosphorus. They're really close. And then antimony, SB, is 2.05. So again, in general, the pattern is as you're within a family, it decreases as you head downward. And another pattern I want to bring to your attention is that if you look at the second period, the second row, right? A period is a row. Lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. Notice there's a pattern there, which is the electronegativity value increases as you move from left to right, away from metals and toward the nonmetals. You can think of it this way. The further to the right you go, the more non-metallic the element becomes. So fluorine, 3.98, is highest in that row. It's highest in that period. Lithium, 0.98, is the lowest. The more metallic it is, the lower the electronegativity. The more non-metallic it is, the higher the electronegativity is. Fluorine is actually the highest value in that entire table, 3.98. It's very close to 4. And if you compare it to the other elements, francium is the smallest, all the way down on the far left at the bottom, 0.7. Fluorine is the highest value, really by far. Oxygen, 3.44, is the next highest, right? It's actually pretty high too, 3.44. Followed by nitrogen and chlorine, which are similar. Chlorine's actually the third highest at 3.16. And then nitrogen is the fourth highest at 3.04. So those four, that little L at the right side of the periodic table, nitrogen, oxygen, fluorine, and chlorine, those are the most electronegative elements. And for those of you that are biology majors, of course, you're interested in this idea of hydrogen bonding, right? It comes up a lot when you're talking about how DNA, the structure of DNA interacts, and how proteins interact with each other, the amino acids within proteins. That hydrogen bonding is important for those, right? Well, it's those elements on the right side. It's the nitrogen, it's the oxygen, it's the fluorine and the chlorine. Those are the ones that are involved in hydrogen bonding, the most electronegative elements. Now, fluorine, because of the fact that it can only form one bond, so it really can't form very complicated substances, you don't generally see it in biology because it's just not one of those elements that's that useful biologically. So nitrogen and oxygen, on the other hand, have the capacity to form 2 bonds or even 3 bonds or even 4 bonds in the case of nitrogen. So hydrogen bonding is much more diverse in terms of those. But to a chemist, fluorine is an important element in terms of consideration of hydrogen bonding. Chlorine as well, although generally it's not considered for hydrogen bonding because, again, well, chlorine has its own kind of issues. It's in the 3rd row, so that changes its chemistry a little bit. But technically speaking, chlorine is capable of hydrogen bonding as well. Okay, so 2 patterns. Within a family, remember a family is a column, it decreases as you go down. And then the second pattern is that it increases as you go toward the nonmetal across a period. So smallest with lithium and sodium and potassium, largest when you get to nitrogen, oxygen, and fluorine. Okay, those are essentially the 2 patterns. Now, I'm going to get rid of the this version of the table, and I'm going to write down a few numbers that I find useful. And that is this. To have hydrogen at 2.2. And notice I'm not going to use that extra sig fig. I'm not going to put 20 or 2 after the decimal. I'm just going to round it to 1 because, to be honest with you, we don't need that many sig figs for this consideration. And then what I'm going to do is I'm going to do lithium. And I'm going to put lithium at 1.0. So remember, it was 0.98. But if you round that to 1 digit past the decimal point, you get 1.0. Okay. And then for beryllium, 1.5. I'm going to ignore the transition metals completely. We really don't need to worry about them for this discussion. So let's ignore them and head straight over to boron. Boron is the first element. That's in group 3A. First one on the right side, 2.0. Carbon, 2.5. Nitrogen, 3.0. Oxygen, 3.5. Fluorine, 4.0, right? And then for chlorine, I'm going to come back and put that at 3.0. So these are just a few of the elements, right? But for those of you that are biology majors, or if you're a polymer chemist, for example, or a food chemist, these are important elements, right? Hydrogen is important, certainly. Carbon is important in organic molecules. Nitrogen and oxygen are as well. And so notice there's a very simple pattern here in this second row. And that is with lithium, it starts at 1, and it just increases by a half for each element that you go over, right? So 1, 1.5, 2, 2.5, 3, 3.5, 4. And then for chlorine, it jumps back down to 3. But again, the most electronegative elements are these 4 right here, okay? So if you just remember a few things, which is 1, as you go down, it decreases, right? So all the way down to francium, we said it was 0.7. And then if you remember that it increases as you go this way, that means you're going to get the most electronegative elements up here in the top right corner, right? The nonmetals. Those will be the most electronegative. The least electronegative are actually these ones in the first column. Those ones are the least, right? So it's true, francium is smaller than lithium, but they're not that, they're both pretty small, right? All of those alkali metals are small. Hydrogen is in between. And that leads to some interesting qualities of hydrogen. What it means is it's not extremely electronegative, but its value is more like a non-metal than it is like a metal, right? The metals we see over here are 1, 0.9, 0.8. Some metals, the transition metals, are a little higher. They're 1.7, 1.8, 1.9. But hydrogen is a little bit higher than that. It's about 2.2. So that puts it sort of in between these elements here, right? So in a sense, even though hydrogen is in that first column, its electronegativity value suggests that its chemical properties are a little bit more like a nonmetal. And so that's why we get to see these really fun organic molecules, right? These organic molecules are a result of hydrogen and carbon and oxygen bonding covalently, okay? And that covalent bonding is connected. to this issue of electronegativity. Okay. So you can always refer to a table. You can just type in the electronegativity table. And typically we tribute Linus Pauling with this because he was really the first one to develop a full table of electronegativity values. And you can look that up, but it's actually probably for most chemists more useful, particularly if you go on to take organic chemistry, it's more useful just to sort of see these patterns, right? That it increases as you go to the right and it decreases as you head down, and that your lowest values are over here and that your highest values are over there, okay? So how do we use these in electronegativity values? How do we use them? Well, here's the simplest thing we can say. What we do is you take the difference in, I'm going to just abbreviate it EN for electronegativity. You take the difference in electronegativity values between the atoms in the bond, between the two atoms. And then if this difference is greater than, I'm going to use the greater sign, 0.4, the bond is polar. Okay, so if you get a difference of greater than 0.4, I'm sorry, I'm going to put greater than or equal to 0.4. Okay, my own kind of personal opinion. If it's greater than or equal to 0.4, the bond is polar. Okay, so right there, all that tells us something very powerful. If we want to know whether this bond has electrical properties, that of being a dipole, all we got to do is look up these electronegativity values and take a difference. Just subtract the 2, right? 2, if the difference is less than 0.4, the bond is non-polar. It will not have electrical properties. We can ignore its electrical properties. Okay, so that's powerful as well. 3, if the difference is greater than 2, not greater than or equal to, but greater than 2, the bond is not even covalent. It's ionic. This allows you to predict whether a bond is ionic or covalent just by looking at the difference. Okay? So let me show you a couple examples. Let's try F2. Let's try OH. And let's try, actually, let me write it this way. FF. And then let's try NaCl. Okay. What we're going to do is we're going to determine whether these bonds, I have 3 bonds shown there, whether they are polar, nonpolar, or ionic. In fact, let's do it this way. Nonpolar, polar, and then ionic. Okay, those are our 3 options. Okay, so let's do FF, the fluorine-fluorine bond. I'm going to look the values up. Fluorine is 4.0. Okay, so what do? You take the difference between the two. So fluorine is 4.0. Oops, I don't want to write it over there. So let's do it. I guess I'll do it over here. I'm going to do this. Okay, let's do it here. Fluorine is 4.0. And so they're both 4.0, right? It's two fluorine atoms. So if they're bonded together, they have the same electronegativity values. Well, what happens? If you take the difference, you get 0. Exactly, right? It's got to be 0 because they have the same electronegativity values. So this one would be nonpolar. Okay? It's nonpolar because it doesn't have any electronegativity difference. It's got to be greater than or equal to 0.4 to be polar, and it's got to be greater than 2 to be ionic. So that's a nonpolar molecule. So what we would conclude is that if you put F2, FF, right? If you put that into our little experiment here where we have the positive voltage and the negative voltage, the F2 would be unaffected by that electric field. Wouldn't be affected at all because it's neutral. Not only is it neutral, it is nonpolar. There's no electrical dipole there. Okay. Let's try OH. OH, well, OH, let me erase this. Oxygen is 3.5, and then hydrogen we said was 2.2, right? Now, you take the difference. Now, sometimes people say, well, which one do I subtract from which? And it really doesn't matter. You're just looking at essentially the absolute value. What is the difference between the two, right? So whether you take the 2.2 minus the 3.5 or the 3.5 minus the 2.2, either way, just take the absolute value of it. We're looking for the magnitude of the difference, okay? So 3.5 minus 2.2, that gives you 1.3. Well, right there, that's in this category of greater than 0.4. Greater than or equal to 0.4, but it's still less than 2, right? So that would put it in the polar category. So OH is a polar bond, which means that if you had OH in this machine over here, in this experiment, those molecule or those bonds would rotate so that so that one of the atoms was on the negative voltage and the other one was on the positive. Okay. And then what about NaCl? Let's do NaCl. Now, we already know NaCl should be ionic, right? It's a metal with a nonmetal. Metal with a nonmetal is generally ionic. Sodium chloride, we know that's ionic. You throw it in water, it dissolves, forms ions. We talked about that at the beginning of the course. But if we look at this table, sodium is 0.9 and chlorine is 3.1. Or 3.0, I'll use 3.0. Okay, let's do our difference. 3.0 minus 0.9, what do you get? You get 2.1. So right there, that's greater than 2, right? If it's greater than 2, it's ionic. So the electronegativity values very simply allow us to determine whether a substance is ionic or not, okay? And what you find is that the alkali metals have small enough electronegativity values that when you combine them with a halogen like chlorine or fluorine, you get ionic. It comes out as ionic. Okay. Now, one more thing to mention, which is we do have this idea that a dipole has a positive end and it has a negative end, right? That's our dipole. So when a bond has a dipole, we say it's polar for short. Which one is positive and which one is negative? And the answer is the negative end is the more electronegative atom. And the positive is the less electronegative atom. In fact, some people use the term electropositive. They would say that the less electronegative atom is more electropositive. So if we were to have lithium and oxygen, I'm sorry, 1.0 and 3.5, right? Now that's going to be ionic, right? The one that's less electronegative, right? This is less electronegative. That one's going to be positive. And the one that's more electronegative, that one's going to be negative. Okay. So if I were to do OH, for example, there's OH. I'm going to write the electronegativity values below. Right there, because this one's higher, we know this is the negative end. And since this one is smaller, we know this is the positive end. Okay, so O is negative and H is positive. And those charges are equal to each other, right? The oxygen has the same amount of negative charge that the hydrogen has positive, so that they neutralize each other. Overall, it's neutral, but there's charges within it. Okay. Sometimes you will see a symbol, the delta symbol, instead of just the negative and the positive. So you'll see delta negative and delta positive. This is delta. It's the Greek letter delta, lowercase. And in this context, delta means small. It's used in calculus, actually. If you go on to take calculus, the symbol delta in this context is meant to be small, okay? So what that means is there's a small negative charge. It's not big. It's not -1 or -2. It's small, like -0.1 or -0.2 or -0.3. Okay, they're small charges. So sometimes you'll see it in this notation. Sometimes you'll see it in this notation. Okay. Let me see if I can bring up an Alex problem. Okay. So this is predicting bond polarity. And so we're going to be given a Lewis structure. So this is the Lewis, this example, it's the Lewis structure for carbon dioxide. Okay. Now the question is, so the way they do this is they highlight one of the bonds in red. And then they ask you a couple of questions. One is the highlighted bond polar? Okay. And then they ask you which atom in the bond is more negative. Okay, so let's try this one right here, for example. So the highlighted bond is this over here, right? That's your highlighted bond. So we look the values up. Carbon is 2.5. Oxygen is 3.5. Okay. So is it polar? Well, we take the difference. 3.5 minus 2.5 is 1.0. That's certainly greater than 0.4. So there's no question it's polar. That's going to be a polar bond. So yes, it is. It's polar. And which atom is more electronegative or more negative? Well, the one that's negative, the one that's more negative, is the one that's more electronegative. That's really what it means. So the oxygen, it's the one with 3.5. So this one is the more electronegative one. So it's more negative. So the answer is the oxygen atom is more negative. Okay. If the question were which one's more positive, then it would be the opposite. The one that's more positive is the one with the smaller electronegativity, which is this one right here. So you end up with an interesting thing here. Now these molecules have dipoles. They have these electrical properties within them, and those electrical properties will affect how they behave chemically, physically, all sorts of different ways. It leads to a lot of interesting discussions, this consideration of electronegativity. Okay. So we'll leave that electronegativity for now. It actually is an important issue in terms of drawing Lewis structures as well. But we'll talk about that when we get to formal charge. Okay. So what I would like to do now is I'd like to talk a little bit about formal charge. Formal charge. Okay, so Let me see if I can bring up here something. Okay, good. All right, so formal charge is first and foremost, it's a calculation. It's a calculation that you do. It's actually a pretty simple calculation. It's just addition and subtraction, not even multiplication, but it is a calculation. And we use, this is formal charge. We use formal charge it's used to evaluate Lewis structures. So for example, okay, so here's the Lewis structure for O2. And you already know that there's something wrong with this Lewis structure, right? It has the correct number of electrons. O2 has 12 valence electrons, and this one has 12. But there's another problem, and the problem is the octet rule, right? Each oxygen has 3 bonds, so that's 6 electrons. A lone pair, so that's 8 electrons. But each atom also has 1 extra electron, right? This one over here, which makes it a radical. So each oxygen atom has 9 electrons. That's a violation of the octet rule. So we know that Lewis structure is not that good. It's problems anyways. So if we were to draw it this way, only have 2 bonds and 2 lone pairs. Now we've solved the problem. Now each oxygen has 2 lone pairs, which is 4, and 2 bonds, which is 4. So that's an 8 electrons for each. So this one's good. And we're using the octet rule to evaluate that structure. Now what I'm going to claim is that there are structures that we can draw which are perhaps incorrect, and we can use another method of evaluation, which is called formal charge. So for example, some might argue that, let me see if I can do this. Oh, yeah. That the phosphate ion, so I'm going to draw a Lewis structure for the phosphate ion. So this is phosphate. Some might argue that this is a proper Lewis structure because it obeys the octet rule. The oxygen atoms have 8, and the phosphorus at the center has 8. Okay, so based on the octet rule, we would suggest that this is perhaps an appropriate structure. However, there is evidence that this is a better Lewis structure. Okay, this one over here on the right. There's evidence that this is a better Lewis structure based on the strengths of the chemical bonds and so forth. So the question then would be, well, this one's a violation of the octet rule. So how could this be a better Lewis structure? Well, there's evidence that it is. So we have to base our theories in reality, right? We can't just make up a theory and then argue it's true because we want it to be true. It turns out there's certain structures that violate the octet rule, or at least appear to. So for that reason, we need another method of evaluation. And that other method of evaluation is called formal charge. Okay. And so what I'm going to do is I'm going to show you how to do the calculation first. So the first step is just how do you calculate formal charge. Okay. So it's a little tricky. You have to be very careful. You have to be very precise. And I'm going to try to be precise in my language of how you calculate formal charge. It's very easy to get the wrong answer, even though it's a seemingly simple calculation. Here's what you do. I'm going to take carbon bonded to oxygen as an example. Let's not do a triple bond. Let's just do a double bond. Okay, carbon dioxide, right? So first of all, you do the calculation for each atom separately. Each atom is given a formal charge value, okay? So 1, calculate for each atom. Just like you do for the octet rule, right? You're counting the electrons around the atom, the octet rule. You do that for each atom, right? Okay, so you do it for each atom. Now, how do you calculate it? Here's what you do. From the periodic table, you look up the number of valence electrons. So that's your first step, okay? So I'm going to do it for these 3 atoms, right? Let's do it for all 3 of them, OCO. Okay. Oxygen is in group 6A, so it has 6 valence electrons. Carbon is in group 4A, so it has 4 valence electrons. Oxygen is in group 6A, so it has 6 valence electrons, right? So we've already done that. We already know how to do that. You just look them up, and now you have the number of valence electrons. Third step. What you do is you count the number of electrons in the Lewis structure. So now you're not using the periodic table, you're using your Lewis structure. So this presupposes that you already have a Lewis structure, right? So you draw a Lewis structure and then you do this formal charge calculation. But you count the electrons differently than we have so far. Previously, a chemical bond is 2 electrons, and both atoms get to count those electrons. In formal charge calculations, we don't do it that way. We do it differently. We assume that the bond is equally shared by both atoms, so each atom only gets 1 of those 2 electrons. That's the fundamental difference in counting here. A bond doesn't count as 2 electrons for both atoms. It counts as 1 electron for each atom, okay? So we count the number of electrons. So a lone pair, right? Remember, a lone pair is 2 electrons. It counts as 2 electrons. And then a bond counts as 1 electron. That's the difference. A double bond, remember a double bond? It counts as 2 electrons. And then a triple bond, it counts as 3 electrons. Okay? Each atom gets that number of electrons. So we're dividing them up, right? So when you do Lewis structures, you don't divide them up, but when you do formal charge, you divide them up. Okay? So now here's what I'm going to do. I'm going to count up the number of electrons for each of those 2 atoms in the Lewis structure. Okay? So let's do it again. So OCO. Let's do this oxygen over here first. It has 2 lone pairs, so that's 4, right? Each of those electrons counts, so that's 4. It has 2 bonds. So remember, the bond, you only get 1 of the 2 electrons. So if you have 2 bonds, you get 2 of the electrons. So you have 2, 4, 5, 6. So that's 6 valence electrons. Okay? Let's do the carbon. The carbon doesn't have any lone pairs, so you don't even count those. But it has 4 bonds. 1, 2, 3, 4. So the carbon gets 4. Okay? This is tricky, right? Remember, if we were doing Lewis structures, you would say the carbon has 8 because it has 4 bonds. But in terms of formal charge, you only give it 1 of those 2 electrons, so it only has 4. And then the oxygen on the right, it has a lone pair and another lone pair, so that's 4. And then it has 2 bonds, so that's 6. Okay? So now we've done our sort of second calculation. We've figured out how many electrons each atom has. Now we're ready to do the formal charge calculation. Okay, so let me, gosh, I'm running out of room, but let me do it over here. So I'll write this as 4. Step 4 is very simple. For each atom, again, you're doing this for each atom, you take the number of valence electrons, which we did as number 2 right here, and you subtract the number of electrons in the Lewis structure. So 2 minus 3. Okay, so valence electrons minus our Lewis structure electrons. So this first group of numbers that we did here from the periodic table minus the second group of numbers that we have right there. Okay, again, you do it for each atom. So we're going to do OCO. Let's do the first one. Well, the first one had 6 valence electrons, and then in its Lewis structure, it also had 6. So 6 minus 6, that gives you 0, right? 6 minus 6 is 0. The carbon had 4 from the periodic table. In the Lewis structure, it also had 4. 4 minus 4, 0. And the oxygen on the right, it had 6 valence electrons, and in the Lewis structure, it had 6. That gives it 0. Now we're going to go into the analysis of this a little bit later. But the main thing we would say is that if we draw a Lewis structure and the formal charges are 0, that suggests the Lewis structure is valid. It doesn't prove that it's a good Lewis structure or valid, but it suggests that it's a good Lewis structure. Okay, so for this particular one, we got all these zeros. That is supportive of this being a proper Lewis structure. Not proof, but supportive of it, right? We want to draw appropriate Lewis structures. If we get formal charges that are not 0, that might suggest the Lewis structure is invalid. If we get zeros, that supports the Lewis structure. So we now have 2 tests. We have the octet rule, but now we have this other test, which is the formal charge. So let me show you an example. I'm going to pick one from Alex, and we're going to do a formal charge for each atom. Okay, so here's the example. It's an ion in this case. So this is the Lewis structure they give you. Okay, this is called the azide ion. Okay. And what they want you to do is they want you to calculate the formal charge for each atom. So we have the left nitrogen, the central nitrogen, and the right nitrogen. And then they want you to calculate the formal charge. Okay, relatively simple. So here's how we go about it. Let's start with the periodic table. Nitrogen is in group 5A, so it has 5 valence electrons. Okay, so for each of these atoms, I'm going to write that number down. 5 valence. It's the same element, right? So they're all going to have the same number. And now we're going to subtract the electrons in the Lewis structure. Okay, so remember, the first thing you do is you look in the periodic table how many valence electrons they have. So in this case, they each have 5. And then you're going to subtract off the number of electrons in the Lewis structure. Now remember, I'm going to put this in parentheses because remember, a lone pair counts as 2 electrons, but a bond only counts as 1. A double bond counts as 2. A triple bond counts as 3. So we're going to have to add a couple of numbers here to get that. So I put it in parentheses. So let's start with the left nitrogen. The left nitrogen has a lone pair. That's 2 right there. and it has 3 bonds, so that's 3, right? Let's do the central nitrogen. The central nitrogen doesn't have any lone pairs, but it has a total of 4 bonds, 3 on the left and 1 on the right. That's 4 bonds. So it's got 4 bonds, okay? So remember, in formal charge calculations, a bond only counts as 1, doesn't count as 2. And then the one on the right has 3 lone pairs, so that's 6, right? And then it has 1 bond, which is 1. So this is interesting. Even though we have 3 nitrogen atoms, they're going to have different formal charges. So let's go through the calculation. In the one on the left, 2 plus 3 is 5. So 5 minus 5 is 0. On the central nitrogen, 0 plus 4 is 4. So 5 minus 4 is plus 1. Now be careful. When you write formal charges, unlike electrical charges like in an ion, here you put the sign and then the number. So don't put 1 plus, put plus 1, okay? With ions, we generally put the number and then the charge, like 3 plus or 3 minus. But with formal charge, you put plus and then the number. The right nitrogen, this one over here on the right, it has 5 valence electrons. It has 3 lone pairs and 1 bond. So 6 plus 1 is 7. 5 minus 7 is minus 2. Okay, right? That's minus 2. So here's, in ALEKS, they don't ask you to evaluate this or analyze it, but here's essentially what we're claiming when we do these calculations. We're claiming that when you draw this Lewis structure, these formal charges are essentially the charges of each atom in this structure. So in this Lewis structure, we've made a azide ion in which the nitrogen on the left is uncharged. It doesn't have any charge. The one in the center is positively charged, and the one on the right is negatively charged. Okay. Where'd the 5 come from? Oh, from the periodic table, right? So that 5 is from the periodic table. Okay. It is often written this way. Formal charge equals valence electrons minus associated electrons. You'll see this. So the valence electrons comes from the periodic table. And then the associated electrons come from the Lewis structure. Okay. And again, the tricky thing for this is that in the Lewis structure, a lone pair counts as 2, a single bond counts as 1, a double bond counts as 2, and a triple bond counts as 3. And then you add up these numbers, and they go in here, associated electrons. This number here, that one comes from the periodic table. Okay, let me do one more. Okay. So again, in this problem, they're going to give you a Lewis structure. In practice, what we would do as chemists is we would say, oh, here's the formula. Let's draw a Lewis structure. And then we're going to use formal charge as a way of evaluating that Lewis structure. The closer these values are to 0, the better. So that previous one we just did, where we had the -2 and the +1, that's not 0, right? So that one may not have been the best Lewis structure. There might have been a better Lewis structure we could draw. Okay. Let's take a look at this one. So we've got the left oxygen, we've got the central oxygen, and we've got the right oxygen. And then we've got the nitrogen. And then we're going to calculate its formal charge. One more point, just quick point to make. When you do these calculations, if you do them correctly, if you add up all the formal charges, they will equal the charge of the ion. So when you do these calculations, if you add them all up, you get -1. It works out very well. Okay. Okay, so let's try. So remember, oxygen's in group 6A, right? So that means it has 6 valence electrons. Nitrogen is in group 5A, so it has 5 valence electrons. So the first number is the number of valence electrons. So oxygen is 6 and nitrogen is 5. So those numbers are coming from the periodic table. And then we're going to subtract the associated electrons, or the electrons in the Lewis structure. This one right here, oh, that's a weird, oh, okay, we'll see. Let's just see how this works, okay? This is actually, I think, an improper Lewis structure, but let's take a look and see what happens, okay? So let's do the left oxygen. It has 3 lone pairs, right? So that's 6, and it has 1 bond, so that's 1. The central oxygen doesn't have any lone pairs, but it has a total of 4 bonds. The oxygen on the right has 3 lone pairs, so that's 6. A lone pair is 2. It has 1 bond, so that's 1. And then the nitrogen has 2 lone pairs, so that's 4. And then it has 2 bonds, so that's 2. So this comes out to 6 minus 7, minus 1. So remember, formal charge, you put the sign first, then the number. 6 minus 4 is plus 2. 6 minus 7 is minus 1. And then 5 minus 6 is minus 1. So this is a terrible Lewis structure, actually, for various reasons. But one reason it's bad, it does obey the octet rule. There's no problem with the octet rule. But look at these formal charges. They're all over the map. -1, -1, -1, +2. None of them are 0. Generally, with the Lewis structure, if you don't get any zeros, there's probably something wrong with it. So this is essentially like claiming in this Lewis structure that you have all these atoms that are -1, and then you have 1 atom that's +2. Now, note, they do add up to -1. That's fine. You know, they should add up to the ion's charge. So that means you did the calculations right. But it suggests it's not a good Lewis structure. Okay? So we'll come back. We'll do some more Lewis structures tomorrow. This is formal charge. So this was section 6.5, I believe. Let me check just to make sure. Oh, no, sorry, this was 8.6. So 8.6. So we've done electronegativity, polarity. 8.4, we've done 8.6 Lewis structures and formal charge. So we'll come back tomorrow and do some more Lewis structures. And we'll look at resonance. And then Thursday, we'll be finishing things up in this chapter with bond enthalpy. Okay? So practice your formal charge calculations, practice your electronegativity calculations, and you should be in pretty good shape with these Lewis structures. Okay? So have a great day. Reach out to me if you have any questions.
And make sure that it's underneath.
Thank you.
And we'll talk later. Bye-bye, everybody.
Bye.